All right, so we're going to be talking about atomic mass now. And we want to be able to define and use atomic mass units. And then if we're given the relative abundances of natural isotopes of an element, we want to be able to calculate the atomic mass of the element. So here we go. So masses of atoms are expressed in atomic mass units. Whoops, sorry about that. So again, masses of atoms are expressed in atomic mass units. And that helps because really the mass of a proton and neutron, like we saw, is incredibly tiny. So it's easier to define mass this way. And it's with units of U here. And U is identified as exactly 1/12 the mass of a carbon-12 atom. Okay? So here's an example of carbon-12 over here. So we have 6 protons, 6 neutrons. So its atomic mass is 12. So 1U is exactly a 12th mass of a carbon-12 atom. So 12U is the mass of one carbon-12 atom. Again, 6 protons, 6 neutrons, and 6 electrons. And since, like we saw in another video, the mass of protons and neutrons are about the same, and the mass of an electron is basically nothing, 12U, again, just reiterating it, is the mass of 6 protons plus 6 neutrons. Okay, so that's an atomic mass unit by definition. So here's the percent abundance of some natural isotopes that are that you could find that is expressed in atomic mass units. Okay, so these are different, again, natural isotopes: carbon-12, carbon-13. We already talked about those. Some potassium isotopes, and you can see that some isotopes are more abundant than others. So basically, all the carbon in the world is C12, or carbon-12, and approximately 1% of the carbon is C13. So same idea with hydrogen and other examples, potassium, etc. Okay, so like I said at the first slide, now what we want to be able to do with this is calculate the atomic mass of an element given the relative abundances of different isotopes. So what do I mean by that? Well, here's an example, the percent abundance of the element neon. So the relative abundance of each isotope is plotted here on the y-axis. So if you just found some neon out there, this is the relative abundance of each isotope. And then the mass to charge ratio is what's plotted down here on the x-axis. And since the plot only shows +1 ions, the mass to charge ratio is the mass of the isotope, basically expressed in U. Okay, so this is neon 20, neon 21, and neon 22 isotopes. Okay, so you can see that most of neon exists, about 90% of neon, all right, exists as the neon 20 isotope. And I don't know, guesstimating maybe like 10% or less of neon exists as like neon 22. Okay, so, and this is just a picture of neon out here, like a neon sign. So how do we do a problem with this? Okay, how do we take this knowledge and solve some problems that we'll encounter throughout the rest of the semester? Okay, so here's an example. So chlorine has 2 natural isotopes. You found a bunch of chlorine in nature, and it's going to have these 2 isotopes mixed in there. About 75%, 75.78% of the chlorine is chlorine 35 isotope. And it gives us the mass right there in atomic mass units, okay, of 34.96885. And then roughly 25%, so 24.22% of the chlorine is the chlorine 37 isotope, which has an atomic mass of 36.9659. So what is the atomic mass of chlorine? Okay, so here's how we're going to do these problems. Okay, so we're going to convert these percentages to decimals. Okay, so we're going to say this is 0.7578%, right? And this is 0.253%. It's actually not percent anymore. That's just what it is when you divide by 100, okay? And then all you have to do is multiply those numbers by the mass of each isotope, okay? And then sum them up. And that's the mass of the chlorine element, okay? So let's do that. So let's say in the first example, or the first isotope, I should say, this is its abundance, okay, times 34.96885, okay? And then this is 0.2422 times 36.9659, okay? So when you do those calculations, for the first answer here, I get 26 point, let's say 50, okay? Again, paying attention to the sig figs here. We have 4 sig figs. That's right, sig figs have not gone away. They're still here. So 4 sig figs there, so our answer can only have 4 sig figs. And then again, when I do this, I get 8.950, I believe. Let me just plug that in my calculator one more time to make sure. 0.2422 times 36.9659. No, actually, that's a 3 there at the end. So there you go. There's an example. You always want to double check your work. Okay. So now what we do, okay, we simply add this up. And when we do that, I get roughly 35 point, let's see, 26.5. I could probably just do this in my head. 8.953. I get 35.45. And that last number there isn't significant with the significant figure rule for addition. And so this is what we get in atomic mass units. And the way you're going to check your answers here, all right, to make sure you didn't do anything weird, is if you just look at the periodic table for chlorine, the number that's listed on the bottom of the periodic table, and this is something we're going to talk about in a later video. I don't know if you could see that. Probably not at all. But if you look at chlorine, okay, it's element number 17 in the periodic table. Its atomic mass, which is listed at the bottom of the box, is 35.45. Okay? So again, this is an example of calculating the atomic mass of an element given the abundances of isotopes. So I think that's it. It is. In the next video, we're going to be talking about the periodic table. So see you there.